Hello. In this video, I want to introduce something called mathematical induction. Mathematical induction. Now, mathematical induction is a method. It's a way we can use to prove a formula, to prove a given formula. So, for example, we already know from the last video, we derived this formula for an AP. But suppose now that we are given this formula, and we need to prove that it is indeed true, that it is indeed the sum of an AP. Well, why would anyone want to do that? Since we've already derived it, why do we still want to prove it? There can be any number of reasons. For example, maybe that I want to double check that it is correct. After all, I've went through quite a few steps involving definitions of symbols and ideas and so on and so on. So it is a way I can use to double check that it is correct. Or it might simply be that this could be a question that we get in the exam and we have to prove it. So for now, okay, for this video, I'm going to take this formula as given. Right? Let's say we are given this formula for the sum to n terms of an AP, and I want to prove it. So the method that I'm going to use is called mathematical induction, and I shall now describe how it works. So given okay, so the problem is this. I want to prove that okay, perhaps let me start by describing the AP or defining the AP. Let's say we are given this AP, given that, say, Sn is the sum of this AP, A plus D plus A plus 2D and so on until A plus n minus 1 D. Okay, that should do, I think. So we need to prove that Sn is given by this formula, n over 2 times 2a plus n minus 1 d. I want to prove this. Okay. And the idea of mathematical induction is this. It involves 3 steps. In the first step, we need to prove the formula or the statement that we're given. We need to prove it for, I mean, the it means it's this. So we need to prove it for n is equal to 1. Okay. Step 2. We assume or pretend, if you like, Well, assume is a more official word to use, but you can imagine that it just means that you pretend. We pretend that it is true. Again, it meaning this equation. Pretend that it is true for n equals to, say, a certain number k. Now this might look a little bit abstract, okay, but think of k here to mean just any number, whole numbers, of course, just any number. So suppose it's true for a certain number k. Okay, suppose that's true for a certain number k. Then in the third step, okay, prove it for n equals to k plus 1. Meaning that basically what we want to show is that if it is true for a particular value of n, which will represent by the symbol k, if it's true for a particular value of n, then this would imply that it is true. We want to prove that this would imply that it is true for the next value of n. Okay, so these are the three main steps, and once we can do this, we can then say that we can then conclude that, because if it is true for n, and then if it's true for any value of k, it must be true for the next k. Then we can say that we have proven that if it's true for 1, and this 2 and 3 will show that if it's true for 1, it must be true for 2. True for 2 must be true for n equals to 3, and so on and so on. So in the step 4, we conclude it is true for all n. So this is the plan, if you like, or the steps for mathematical induction. So let's try that now. So remember what we had to do for the first step. Easier if I just write down the formula first. N over 2, 2a plus n minus 1 d. So step 1, for n equals to 1, is it true? Well, let's write it out. When n is 1, I have Sn, and n is 1, there's a 1 over 2 there, and then I have a 2a here, plus n minus 1, n is 1, so 1 minus 1 is 0. Okay, so half of 2a, which is a. When n is 1, the sum is a. Is this true? Okay, when n is 1, there's only one term, and that one term is the first term, which is a. So the sum of one term must just be a. So this is true. Right, this is true. Okay. So now we assume that it is true. It is true for n equals to k. So I'm going to write this out as k equals to k over 2, 2a plus k minus 1 d. So I'll assume this. Okay. Now with this assumption, I need to prove for n equals to k plus 1. I need to prove this for n equals to k plus 1. So that would be k plus 1 equals to k plus 1 over 2, put n there, and 2a plus, that's k plus 1. So k plus 1 minus 1 is just k, kd. I need to prove this, given that this is true and whatever I've shown previously. So is this true? Okay, let's see how we can do this. Let me start from the left hand side. You know, when you prove an equation, you can start from the left hand side or the right hand side and rearrange things until it looks like the other side. So starting from the left hand side, in this case, s of k plus 1. Now somehow I would need to make use of the previous results or assumption. Okay, that's what we need to do to prove something. We need to make use of what we know. How can we make use of, say, sk, the sum of k terms? Well, we have to think of how this is related to the sum of k plus 1 terms. And the relation is quite simple. The sum of k plus 1 terms is the sum of k terms plus another term. Is the sum of k terms plus one more term. And what would that term be? Well, that term would be the k plus 1 term. Okay, I've summed up the k term, and if I add the next term, I'll get the sum to k plus 1. So the k plus 1 term, what is that? Let me recall the formula for the nth term, or the rth term. Formula for the rth term is a plus r minus 1d. Okay, remember this. So the k plus 1 term would be, right, when r is k plus 1. So a plus k plus 1 minus r is k. So a plus kd. A plus kd. Okay, easier if I make it more clear, hopefully, if I write t of k plus 1. Okay, I have to add one more term to the sum to k terms to get the sum to k plus 1 terms. So that would be sk plus this one. Now, okay, what I should do now actually is I could start using this assumption, because sk is actually this. So this is sk is k over 2, 2a plus k minus 1d plus tk plus 1 is this, which is a plus r minus 1d. Okay, so this is what we have. Now, I remember what we are trying to do. We are trying to prove this, and I started from the left hand side. So that means somehow I must rearrange. I must do something to this until hopefully I can show that it is actually equal to this right hand side. Okay. Oh, I'm missing something. Wait, it's supposed to be the k plus 1 term, right? I've just copied out this formula for the r term here, but I should really have substituted k plus 1 into the r here. If I do that, k plus 1 here minus 1 would just be k. Okay, so that's just going to be k. Let me write this out. So that should be kd. Okay. So how can I put these two together and get this? Right. If I okay, let me just write this out. Let me just expand this. K times 2a, k times 2a, that would be k over 2 times 2a. The 2 and 2 cancel, that gives ka. Okay, ka. Let me write it out over here. So ka plus k over 2 times this. So k over 2 times k minus 1 d plus this plus a plus k d. Well, that should be a minus 1. Wait. That should be a minus 1 from there. Minus 1 d plus that. Okay, a plus kd. So is this equal to this? Yeah, actually maybe. What we can do sometimes is, if it's not so clear how this would look like the left hand side, we might actually start from the left hand side and work backwards, if you like, or work towards this. So let me try this. Okay, I'm going to write out the left hand side here. Okay, it's a bit squeezed. Left hand side, that means this side, is equal to this times this. So the 2 and 2 cancels. I get k plus 1 times a. K plus 1 times a. And then I have this times this. Plus k plus 1 times k times d over 2. Okay, so it's will be k over 2 k times k plus 1 k times k plus 1 times d over 2. K times k plus 1 times d over 2. Okay, so this is it. So now let's take a look at this and this. See if you can find anything similar. Okay, if you look at the a, I have an a here and I have an ka here. Right, so k plus a is k plus 1a. Okay, so this plus this is actually this. Okay, so we have found something similar. What about this? Is this equal to this plus this? Is this plus this equal to this? Well, you probably have to multiply out to see that. Multiply this out and expand this out. Okay, but if you actually do that, you'll find that they would indeed be equal. So what I'm going to do is I'm going to just okay, let me write this out. Let me write this out in full. Okay, so I'm going to need some more space here. See where best to write this. Okay, let me clear this part out. Okay, let me clear this part out as well. Okay, I want to show that this is equal to the right hand side. So now that we have a better idea, I know that I need to group these two together, and I would need to somehow rearrange those two. Okay, so I'm going to continue from here, from the left hand side. Now I'll group those this and this together, this and this together to give me k plus 1a. Okay, plus, and these two, right, you see I have a k and a d here and a k and a d here, so those two are common factors. So let me from this and from this, okay, let me take out a factor of kd over 2. Okay, kd over 2. So if I take out kd over 2, I have k minus 1 from here. If I take out kd over 2, alright, if I take out kd over 2, I can imagine that I put an over 2 here and a times 2 here. So I'll get a 2 here, plus a 2. So this is what I would get. Okay, so k plus 1a plus, now that simplifies to k plus 1. So k d over 2 times k plus 1. And now you see that I have k plus 1 and k plus 1 here as a common factor. If it's always good to have a look at what we are aiming for, and we are hoping to show that this is the same as this right hand side. So let's see what we have in common. Okay, I have a k plus 1 and a k plus 1 here, and I have a k plus 1 here. I have all the a, d, and d down here and here. I need to get this to look exactly like this, right? So if I have k plus 1 here and here, I can factor it out. Like what we have here, that is factored. That is a factor in this expression. But I have an over 2 here as well. And I have over 2 here, but I don't have an over 2 here. But I can make an over 2 here if I just do, say, 2 over 2, right, which is 1, which is the same. Okay, so we have k plus 1 over 2 here, and I can factor out k plus 1 over 2 and k plus 1 over 2 here. So I can think of k plus 1 over 2 as a common factor. Okay, so this would be equal to, okay, I'm going to factor out k plus 1 over 2 now. K plus 1 over 2. So if I do this, what do I have in the bracket? Factor out k plus 1 over 2, I have 2a from here. Factor out k plus 1 over 2, I have kd. And they are exactly the same. They're exactly the same. Oops, something has happened here. But you can see that this is the left hand side and this is exactly equal to the right hand side. So I've just proven I've just proven that this statement is true. So therefore we can conclude that by mathematical induction the formula for the AP must be true.